So we are learning about the out-of-order process architecture. So actually, this is the very important architecture. And then because, so as I mentioned, the modern process architecture employs this out-of-order process architecture with speculative execution. So this is actually the backbone. So it's a very important structure or important architecture of the modern processes. Okay. So in order to understand the architecture of out-of-order processor, then you need to understand how the Thomas law algorithm works, and then you need to understand the some important hardware component of the speculative execution. So actually, this ROB, so Leo the buffer, is the main feature of the speculative execution, because with the ROB, then we can temporarily store some intermediate result. So which means that the execution of the instructions can be processed out of order, but in order to execute the many instructions, so actually, so there are many instructions. We can find many instructions in our normal applications, and then so these instructions have data dependencies. So which means that the later instructions use the result of the former instructions. So which means that the executed result should be stored in a processor. And then which means the following instructions use these stored result of former instructions. The problem is that, so I already mentioned that the problem of the issue of the Thomas law algorithm is branch instructions. So which means, so with the original Thomas law algorithm, we cannot execute the instructions over branch instructions. So which is why? So you need to understand that in the process, also I repeatedly mentioned that processor, when an instruction is executed, so and then programmers think that every instructions are executed atomically. So the result are updated immediately in the processor, and if the instructions are executed. So, but it's not true in the real hardware. So the performance issues in Thomas law algorithm is that the result of the executed instructions are updated to register file or also in the memory, so immediately. So, and then that's the problem. So and then so in today's class I will explain about some branch predictor. So and then when a branch is executed, so if the processor encounters a conditional branch instruction, and the execution path of our application is diverged. So it's divided into two paths. So we need to select the one of these two paths, but we don't know about the future. Actually, the processor doesn't know about the future result of the branch instructions. So with the Thomas algorithm, when the branch instruction is encountered, then the processor stop executing these branch instructions after this branch instruction. Okay, that's the actually significant performance bottleneck of the Thomas algorithm. And then in order to overcome this bottleneck, the speculative execution is employed in the Thomas algorithm. And then the main component that realized the speculative execution is ROB, so it's Leo the buffer. So you can understand that with the ROB, we can we can distinguish the completed instruction and committed instruction. Okay. So committed instruction means that the process already knows the result of instructions, but these results are not reflected on register files or memory. Okay, because I explained that when an instruction is executed, then the state of a register file and then memory are changed. Okay, so and then I hope everyone can understand the instruction execution of instruction timing, like this table. So with this table, then we can figure out how instructions are executed and committed in the Thomas law with speculative execution. Okay, so as I said, there one column is added to the Thomas law algorithm, so it's a retire or committed part. So before this instruction is committed, then the result of this instruction are stored in the real buffer. Okay, so we can split some registers and then real buffer. So so we will take midterm exam. So actually, maybe the early June. So and then this timing table will be, you can find this timing table in the midterm exam because it's very important. So we'll try to understand how the speculative executions are implemented on Thomas law algorithm. And then, so on the today's class, I will explain about the register renaming and branch predictor. So first, I will explain about the register renaming because this register renaming is tightly related to the Thomas law algorithm with speculation. So if we see the architecture of a Thomas law algorithm, then we can find that the result, actually, when an instruction is executed like this one, add R1, R2, R3, then we can use operands of this instruction from register file, right? So actually, the main purpose of a register file is to store operands of an instruction, and then the register file is very fast, so we can read the operands from register file very quickly. So that is the purpose of a register file. But in order to implement the out-of-order execution and speculative execution, then the operands of an instruction can be also stored in the register file. Also, the operands of instruction can be found in the ROV because before an instruction is committed, the result of instruction is stored in the ROV. Also, so when I explain about the Thomas law with speculative execution, I said that the register has three states. What are those three states? So completed, committed. So when an instruction, so when this register is committed, then we can find the data of this register in register file. So it's like a normal state. normal so normal states of the static pipeline architecture. So actually we can find the operands of the instruction in the register file in the statically scheduled pipeline architecture. And then another state is the completed. So in this case, we can find the data of the register file in the ROV. Okay, so I already mentioned that before the register is committed, the completed result is stored in the ROV. And then another location. So another state is that it's dispatched, but it's not yet completed. So not yet completed. So if the register, if we don't know the result of the register file, so it's just the register. This ROB entry is tagged in the issue queue. Okay, and then in order to implement the data forwarding, got it? So the ROB entry number is tagged in the issue queue, and then if these operands are ready, so which means that the instruction that generate the result of this operand completes in the processing unit, then the data is forwarded to the issue queue. What does that mean? We also need to store operands of this register, the data of this register in the issue queue, right? So what's the problem? It's a cost issue. So it means that the required operands can be stored in the original register, in the register file, ROB, so in the issue queue. So, so register file is also very fast, and then in order to support the quick, very fast execution, then ROB also is work very quickly. Also, the issue queue is the same. It's just kind of memory component that works very fast. Okay, because the processor works very fast. So what's the problem? Cost issue. Operand, the required operands can be stored in different components, the kind of register file, LIODO buffer, and the issue queues. But in order to implement this Thomas algorithm with speculation, then we need to assign the storage space for these operands. Okay, in register file. Obviously we need to have the architectural register file, right? So, but we need the additional space for additional space for operands in ROB also is queue. So that's the cost issue. And how can you solve this problem? It's register renaming. So the first, I said that the main purpose of a register file is to store the temporary data. So it's not actually temporary data because the instructions access register file. But the most of the data required by applications are stored in the main memory. And then why do we use register file? Actually, because of performance issue. But so So it's a memory hierarchy. Then the register 5 is here. So it's the top of the memory hierarchy, which means that the register 5 is very fast, but it's expensive. The cost is very high. So size is very small. So main purpose of the register 5 is to store operands of instructions. That is the main purpose of register 5. And then we can access this register 5 very quickly. So and then the processor can access register 5 very quickly. So this is the main feature of the main feature of register 5. It's small and very quick. It's very fast. Problem is we need a large space in ROB and issue queue. So which means it's expensive. So ROB also should be very fast. So which means that we need to access the data in ROB very quickly. Also, the issue queue is a kind of it's a memory component. So it's a queue, right? So it's also expensive. Then how can we reduce some cost for this operand space in ROB and issue queue? So we can say that this register is the architectural register. So what does that mean? Number of registers is defined in actually instruction set architecture, right? So in RISC-V, we have 32 general purpose integer registers, also 32 floating point registers. So if you read the ISA instruction set architecture manual, you can find that the number of architectural registers is defined in this ISA manual. So this is the architectural registers. So it's defined in instruction set architecture. Then so you can think like that. So how can we implement the out-of-order processor? So Thomas algorithm. So how can we implement the Thomas algorithm? We can implement Thomas algorithm with actually register renaming. So what does that mean? So this means that, so actually like this, add R1 and then sub R1. So these R1 are destination registers of add and sub. But we can know that the result of this add and then the result of sub are different, even though they are storing the result to the same architectural register, but the update, so these registers are updated by different instruction. So which means that we need to distinguish this case, right? So which means that, so R1 updated by add is different from R1 updated by sub. So in order to implement this, we need to employ register renaming actually. So which means that we need to distinguish R1 of add and the R1 of sub. And then as I mentioned, so Thomas algorithm with actually implicitly apply the register renaming with the tag number. And then in the speculative execution, we also implicitly employ the register renaming with ROB entry number. Okay. So we can apply the similar approach for register renaming. So which means that this is the architectural register defined by ISA can be different from physical register in a processor. So we can implement register renaming with the different physical register number. Do you understand? So what does that mean? R1 of add can be mapped to the like a physical register number P1, and then R1 of sub can be mapped into the different physical register number P2. So which means we can make the large physical register file, and then in this physical register file, there are more registers. So in the ISA we can find several. In the ISA we can find several architectural registers like R1, actually R0 to R31. But we can prepare the more physical register file like P1 to P127, for example, like P0 to P127, and then we can map this R1 of the add to the different physical register P1. Also, we can map this R1 to the different physical register like P2. Okay. Then what is the benefit? Benefit means that we don't need to store the intermediate result in the ROB or EQs. Okay. These results can be found in the larger physical register file. Okay. Then we can also distinguish the states of these registers. Okay. Some registers, physical registers. So for example, let us assume that R1 of add is committed. So state of this R1 is committed. So that means that then we can use the P1 as the committed register value. And also let us assume that R1 of sub is completed but not yet committed. Then we can use this P2 as some operands of the following instructions, out of the processor. So that is the idea of register renaming. So which means we can make the very large physical register file. It's the size of this physical register file is larger than the size of architectural register file. So which means the same architectural registers can be mapped to the different physical registers. Okay, because we need register renaming for out-of-order processing, and then we can map these different architectural registers to the different physical registers. Okay, this is the idea of register renaming. Okay, so I already explained. So this is so in order to implement the register renaming concept in the speculative Thomas loop, then we need the two register alias table RAT. Okay, so there are front end RAT and then retirement RAT. So when I mention the state of the register file, so it's very important. It's like committed. So committed means that this architectural state is updated to the register file. So, and then another state is the completed and it's being executed. So which means that it's dispatched, but it's not yet completed. So what does that mean? If an instruction is dispatched, then so like let us assume that add R1 is dispatched. Then the following instructions need to use this destination register of R1. So in this case, we need to convert this architectural register number of add R1 to the different physical register number like P2, and then the following instructions need to use the P2 instead of R1 because this add instruction will store the result to the R1, and then the following instructions like following add, following sub, like R1 need to use this value. And then let us assume that another instruction like sub mul instruction try to update the value to the R1. So in this case, this R1 is different from the R1 of this add instruction. So it is mapped to the P3, the different physical registers. And then after this instruction, the next instruction, the next dispatched instruction that use this R1 need to access the P3. Okay, so what does that mean? So we need to track the latest register. Register by dispatched instruction, because after this instruction, then the following instruction will use this register. Okay, so there are two, but we need to also know the committed register. Why? Not to support the speculative execution, then we need to know the committed register. So if the speculation fails, then we need to roll back to some speculation point. And then in order to implement this speculative execution, we need to know the committed state. So we need to know the committed register. So that's why in order to implement the register renaming, we need two register alias table. So like front-end RAT, the front-end RAT stores the latest value. So which means that the registers, the destination register of dispatched instruction. Okay. And then we need to also store the retirement register, so retired value. So it is, so this register is stored in the retired register alias table, RAT. Okay. So there are two RATs in the register renaming. So the front end RAT and then the retirement RAT. Okay. These are main points of the register renaming. So if you see that this enhanced Thomas law, speculative Thomas law, then you can find that this is the physical registers, and then the size of the physical register is large. Physical register file is larger than the architectural register file, and then we have the two register alias table. It's like the front end RAT and retirement RAT. Okay. What's the problem? Oh, it's interesting. So, and then very interesting. What happened? Oops. Okay. Okay. And then the another step is the register fetch. So with the register renaming, why do you use the register renaming? In order to reduce the cost. So the cost for storing some temporary values in ROB or issue queues. So which means that we can read operands from physical register file. Okay. So all operands required by instructions are stored in the physical register file. So which means the size of the physical register file is larger than the architectural register file. But so we can reduce some data space in the ROB. The ROB entry number is very large also. Also, we can reduce the data space in the issue queue. So issue queue is also large. So which means the temporary value. So temporary value means that it's completed, but it's not yet committed. So we can find these data in the physical registers. So which means when the instruction is issued to the processing engine or processing units, then we can fetch the operands of these instructions from the physical register file. So in this enhanced Thomas law algorithm, then the new stage, so additional stage is included. So this stage is called the register fetch. Also, which means that so like add R1, R2, R3. So it also assumes that this instruction is executed. So when this instruction is executed, like add R1, R2, R3, then you can find that, oh, this is the destination register of this add instruction. And then these are the operands of this add instruction. These are source registers. So which means that we need to read the data from these R2 and R3. So when this instruction is dispatched, so is dispatched. So the destination is the R1 and then the source are R2 and R3. So we require to read data from the R2 and R3. So in this case, we check the front end RIT. Okay, so we check the front end RIT like this. So R2 is here, and then check the front end RIT. Then we can find the physical registers that is mapped to this R2. Okay, like let us assume that this is the P100, and then also we can access the front end RIT of R3. So we can get the P like 210 here, and then this R1 is dispatched to the front end RIT for this R1 is updated. Okay, like P101. So when the instruction is updated, then we need to get the physical register numbers of the source registers. So we need to update the front end RIT. So which means, when this instruction is dispatched and then instruction is enqueued in the issue queue, so it is translated like add P, not this one, R1, and then P100, and then P110. Also, in order to update the retirement RIT, the ROB entry number is tagged in this instruction. Okay. So, and then let us assume that P100 is done by formal instruction. Okay. And this instruction, so the formal instruction complete to get a result for this P100 is R2 actually. Then, the result is given to the GDB, and then this result is stored in the actually physical register file in P100. Okay, so this is the physical register. So, and the R2 is mapped to the P100 for the formal instruction. Then for this instruction, the result is stored in the P100. And then at the same time, the state of this P100 is changed to the ready. And it's the same to the P110, P110. So it's the same to this R3 is a P110, and the result is ready. So it means that the result is completed by formal instruction. Then it is marked as the ready. So which means that this result is found in the physical registers. So all source registers are ready, then this instruction can be executed. So which means when this instruction is ready, then we need to fetch the data from the physical registers. So we need the register fetch stage. So when the instruction is issued, the data is fetched from the physical registers and then it's executed. Okay, that is the register renaming with the speculative Thomas law. And so what's the problem of this register renaming? So I believe so you can understand how the register renaming works in the speculative Thomas law. And then so the one of the disadvantages of this register renaming is that we need to add one more stage for register fetch, and then it will also take clock cycle. So which means that the latency of instruction is increased. So that is the some disadvantage of this register renaming, but you know, it's like the pipeline stage is just added, so it's not a big deal. And then, but the problem of this register renaming is when the branch is mispredicted. So which means that when the speculation fails, then this rollback mechanism is a little bit complex. Okay, so problem is that then with the register renaming, with the register renaming, we need to store the front end RAT and then retirement RAT. So which means that is the committed registers are stored in the retirement RAT, and then the dispatched registers are stored in the front end RAT. But when the speculation fails, how can we know the speculation failed? So which means that this is the dispatch point in the ROB, and then this is the commit point. So, and then also, you know, there can be many branch instructions between this commit point and then dispatch point. So, and then, you know, one of the speculation may fail, so which means that we need to roll back to a certain point of the reload buffer. Okay. Then, how about the register alias table actually? When the state of the processor is restored to the previous point, then which means that we need to also recover the RAT at this point. Understand? So you can understand how the speculative execution works. So you know the state of a processor should be recovered. So the main idea of out of the processing means that we can select some predicted path in the instruction. So which means that when the instruction is executed, the state, like the not architectural state, the micro architectural state of a processor is changed. So I mentioned that. So you need to distinguish the architectural state and micro architectural state, and then these are different. Okay, so architectural state means that the states on register file and main memory are changed. So that means the states on register file and main memory. But microarchitectural state means it's some every state in the processor core. So which means the state of issue Q was a state of ROB, the state of also register alias table. Okay, so you need to execute some instructions. Actually, the every state of this processor is changed. Okay, but it's not committed because so we need to the main idea of this out of the processing is distinguishing architectural states and microarchitectural states. So what I want to say is when the speculation fails, then we need to roll back to the previous states of a processor. So it's a microarchitectural state. So which means actually RAT is the main part of these microarchitectural states. So which means we need to roll back to the register alias table of at this point when speculation fails. Okay, so this is the speculation point right here. So there can be many speculation points in the ROB, but so we need to recover. So we need to recover this microarchitecture state to the speculation points, the corresponding speculation points. So what's the problem? So main idea is that when speculation fails, we need to recover the two RATs for front-end RAT and then retirement RAT for at this point. But you know, the retirement RAT is the same to this point, but so we don't need to recover the retirement RAT because this retirement RAT just stores the committed physical register number. Okay, and then you know this is same to the at this point. Problem is front-end RAT. So I said we don't need to consider about the retirement RAT because the retirement RAT is pointing this point. Okay, the front-end RAT is updated at dispatch point. So in the speculation points, there can be different front-end RATs. Okay, at every speculation point. Do you understand? So which means, let's think like this. This is the commit point, the ROB. And then, you know, this is the dispatch point. So current front end RAT is pointing the register, the architectural register to physical register mapping at dispatch point. And then the retirement RAT is has the information, the mapping information of from at this point, the commit point. And then there can be many speculation points. SP1, SP2, 1, 2, 3, 4, 5. So, and this speculation point is fails, then we need to go back to this point. So the ROB is rolled back to this point, which means we need to have the front end RAT information at this point. The retirement RAT is the same. Okay. So how can we handle this point? This. The problem is that there can be many speculation points between the commit point and dispatch point. So, and then the we can simply we can simply store the front end RAT at every speculation points. That can be possible. So for example, we can store the front end RATs at this speculation point 1. Also, we can, when the speculation point 2 is detected, then we can store the every RAT for speculation point 2. And then if the speculation fails, then we can recover the front-end RAT from the stored front-end RATs. Okay, that is the very simple recovery mechanism. But the problem, what's the problem? Cost, right? So let us assume that there are 32 architectural registers, and then with the front-end RAT, these 32 architectural registers are mapped to the physical registers. So which means that we need to store 32 entries at every speculation point. So we don't know how many speculations are detected between this commit point and dispatch point. So which means, so this is the very fast and the very simple way to recover the front-end RAT, but the cost, maybe the cost matters. So another mechanism is to rebuilding front-end RAT. So which means, so we can also store some instruction information in the ROB, and then in the ROB, so in the speculation phase, then when the ROB is loaded back to the speculation points, then front-end register file, front-end RAT can be also recovered one by one. So for example, so this is dispatch point and this is the some speculation point. Then we can rebuild this front-end RAT from this point to this speculation point by checking the instruction information stored in the ROB. The problem is that when the speculation fails, we need to restore this front-end RAT information one by one from the ROB. So it will take more cycles. So which means that the speculation fails, then the performance overhead for recovering front-end RAT is a little bit high. It's rather high for this if we use this mechanism. Understand? So this is the a little bit some tricky mechanism. So it means, so register renaming is the very it's a very nice idea. So it means, so we can reduce some data space for the temporary data. So actually it is that the old data can be stored in the physical registers. Actually the structure is also it's a simple, but this rollback mechanism of the register renaming may be a little bit tricky. So based on the rollback mechanism, then when the speculation fails, the rollback may take more cycles. Okay, that is the problem of register renaming. Okay, so this is the enhanced architecture of the register renaming. But you know, most of modern processors applies this register renaming technique, register renaming ideas. So which means that the physical register. So the most of processors has larger physical registers, and then by applying register renaming, architectural registers are mapped to the large physical registers. So that's why in a modern process architecture, the number of physical registers different from number of architectural registers. Okay, so which means we need to distinguish physical registers and architectural registers. Okay. So this is the example of the timing table or when the register renaming is applied. So as you can see, we can find that the one column is also added. So it's a register fetch stage, and then register fetch stage also consume one clock. So actually, and then the other timing is the same, but you need to check the register renaming. Okay. So in the LS, so like here, 1, 2, 3, 4. So also we need to check the data dependency here. So the CD, so it's a completed, then we can issue the instruction, and then after one cycle, the register is fetched. So because the one stage is added, then the timing may be different from the former speculative Thomas law, but actually the baseline mechanism is the same. So the only difference is this register fetch stage. Okay, one clock is consumed. Okay. So I believe you can understand this timing table with this register renaming. Okay. So this is the end of the register renaming. Any questions? Okay, so I complete the one topic. So let's take a 10-minute break. And then after that, so let's talk. We will discuss about the branch prediction, and if we have time, then we can cover the speculative scheduling. Okay. Okay. Let's take a 10-minute break. Okay. So okay. So we are learning about some out of order processing. Some sometimes the pipeline architecture, actually the process architecture. I think my mic is on. So I believe the process architecture is a little bit tricky for some students. So some students are familiar with only software, not hardware. So the hardware architecture is a little bit complex compared to some software. So so I frequently sometimes I say that the software engineers or software programmers work in fantasy world, so actually the virtual world. But the hardware engineers, such as the computer architect or hardware designer, implement some the computer system. So computer system realize the fantasy world, some virtual world on this computer. So actually the fantasy world works on this physical world. So like the process architecture, some physical computer system. So in order to support some very fancy execution environment, and the hardware architect works hardware architects work very hard to implement some very fancy physical world. So that's why the computer architecture or some process architecture is a little bit tricky. And then actually this is the very difficult part of process architecture actually. So the static pipeline is very simple, right? Like the 5-stage pipelining or hazard, so the 5-stage pipeline architecture. So we need to also consider the the hazard cases. So we need to consider the data dependencies or data flooding, but it's relatively simple. But the out of the processor, it is not as simple as the static pipeline architecture. So I believe it's a little bit tricky. So I hope you read the textbook. Okay. So actually, the reading textbook was reading textbook is very important to understand some very complex system. Okay. So please read textbook so to understand what this out of the process architecture. And actually, already 2 years ago. So when I first provide this advanced computer architecture course, so I felt like that students had trouble understanding this Thomas Law algorithm. So actually, I assigned the 1-day class. So and then I explained the Thomas Law algorithm and then the speculative execution. So this out of the process architecture in Korean. so I provide the YouTube link for some summary of the out of the process architecture, and then I explain that this out of the process architecture in Korean. So I provide the YouTube link for this some summary of the out of the process architecture. I hope you can understand it easily with the Korean version. So I know, so English teaching is also, it's difficult for me, also it's difficult for you, but so it's my duty, so I need to teach in English. Okay, so let's talk about the branch prediction. Actually, the branch prediction is another. Okay, so let's talk about the branch prediction. So branch prediction is another core technique in the speculative execution. So actually, if you see this slide deck, you can find that branch prediction is, so you can find the branch prediction part after the simple Thomas Law algorithm. So which means that actually branch prediction is also another core part of the speculative execution. So actually, branch prediction plus ROB, branch prediction plus ROB equal speculative execution, right? So it is because, as I mentioned, the branch prediction is the performance bottleneck of the original Thomas Law algorithm. And in order to overcome this performance wall, then we need to apply the branch prediction plus Liodo buffer. So with the branch prediction and the Liodo buffer, then we can implement speculative execution. So let's talk about the branch prediction. But I believe some of you already knows about the dynamic branch prediction. So this is the dynamic branch prediction, not static branch prediction. So which means that the processor dynamically predict the result of branch instructions. That's why it's called the dynamic branch prediction. So this means that this is the hardware-based branch prediction. So static branch prediction means that the compilers can give the heartbeat. So compiler can predict the result of the branch instructions. So and then based on this help bit, then the hardware performs some branch prediction. So that is the kind of a static branch prediction. But dynamic branch prediction means that the result of a branch instruction is determined by hardware dynamically. So dynamically means that during runtime, okay, while the hardware is executing instructions, the prediction of branch instructions are determined by hardware. That's why it's called the dynamic branch prediction. So we can find frequently the terminology dynamic and static. Okay, so dynamic means it's the during runtime. Static means it's determined by software, which means it's a compiler or some programmers. Okay, usually compiler, not by human. So let's talk about the branch prediction. So why? So when a branch instruction is executed, then the execution path is diverged. So this is the branch instruction, and then based on the condition of the branch, the result of the branch instruction, then this path or another path can be executed in a processor. So I mentioned a path. Why? So when the branch instruction is executed like BQ, then you can find that target of the branch instruction, and then this is the condition of the branch instruction. And if the condition is true, then then PC is changed to the target of the branch instruction. And then after that, some instructions in the basic block are executed sequentially. Then if the branch is false, the result of the branch condition is false, then next instructions. So instructions in this base block are executed sequentially. So what does that mean? This concept is, I said, this concept of basic block concept is very important in a processor because actually we can apply the optimization technique, the compiler optimization technique within a basic block or outside of basic blocks. Okay, so what does that mean? So it's a basic block 1, basic block 2, basic block 3, basic block 4. Let us assume that our code is composed of 4 basic blocks. And then actually, when the first instruction of the basic block is executed by a processor, other following instructions can be executed sequentially. So we cannot find any divergent execution path within a basic block, right? But if we encounter a branch instruction, so we can find the branch instruction in the last line of the basic block, right? You understand? So we can find branch instruction in the last at the last line of the basic block, right? So based on the result of this branch instruction, we can execute the PB2 or PB3. Okay, so it's a PB2 path and then it's PB3 path. So these instructions are executed. So when the branch instruction is encountered, different paths are executed. So this is the basic block 1 is a basic block, 2 can be a basic block 3. So you can find many divergent points as a conditional branches here. So we can find that many divergent execution paths in our program. So what's the problem? So we don't know. So actually the condition of the branch instruction is also determined dynamically. So during runtime, we don't know the exact result of branch instruction. The result of a branch instruction is determined while this code is executed. So the execution path can be this path. Also, the execution path can be this path. So execution path is divergent. So this divergent execution also influences the performance of our computer systems. Then, so in the Thomas law algorithm, we cannot find, so actually we can find many instructions in our code, but the Thomas law algorithm, the branch instruction is encountered. We don't know the result of the branch instruction. So we cannot execute these instructions, nor so we cannot execute these instructions in the different paths like PB3 or PB1. So that's the problem of Thomas law algorithm. Then how can we overcome this as a wall of the branch instruction? We can predict the result. So we can apply the prediction. Or, oh, we don't know. So we don't know the result of this branch instruction. So like true or false. So another possible way to execute the future instruction is to execute these PB2, also execute the instructions in the PB3. And then, so the processor also store the states performed by PB2 and then performed by PB3. And then after the branch is decided, then we can select the one of result. We can apply the same way to the different branch instructions. So possible way to overcome the wall of a branch instruction is to perform every path. And then when the branch is determined, we can just cancel the incorrect path. So we can select the correct path. But this brute force way is requires the very high cost. So it's the large amount of hardware resources. So you cannot apply this brute force mechanism in the branch execution. So another possible way is the branch prediction. So branch prediction is that we can just select the one possible path of the branch by prediction. So we can just execute the one path, not all paths. Okay, we can just execute the one path, and then, but for this branch prediction mechanism, then if this prediction is incorrect, then we need to cancel these instruction. Then we can perform another path. Another way is some hybrid way, hybrid approach. So which means that, if the prediction rate is, so which means the prediction hit rate is very high, then we can apply the prediction. But if the prediction rate is like the 50 to 50, then we can perform the post execution path. Then when the branch is completed, branch is decided, we can just select the one path. Okay, that is the hybrid approach. But the good news in the branch prediction is that the hit rate of branch prediction is very, very high, like it's over 95%. So which means that the hit rate is very high, then prediction is the good approach. Okay, so prediction rate is hit rate is high, we can apply the prediction. We can enjoy the advantage of predictions. Okay, this is also very important. Actually, in a computer processor, many prediction mechanisms are applied, like the memory disambiguation. Also, we can apply the return address stack. Also, many predictions are applied in our process architecture. But why predictions are there? Why do we apply the many prediction approaches? Because prediction hit rate is very high. So in this case, we can enjoy the benefit of predictions. But if the hit rate is very low, like 50 to 50, then we cannot apply the predictions, because what is the disadvantage of the prediction? If a prediction is wrong, then we need to roll back our executions. Then we need to recover to this point. So which means that we need to recover the states of our processor to the speculation point, and then we need to perform again. But this rollback mechanism also consumes cycles. It's a performance overhead. Okay. So prediction is a very good approach, but predictions can be applied only if the prediction hit rate is high. Then how can you apply the dynamic branch prediction? It's simple actually. So I believe some of you already learned about the dynamic branch prediction in the undergraduate course. So okay, so what is the prediction first? Actually, we don't know the future result of the branch, but we can predict by monitoring history of branches. What is the history? It's a previous result. It's the same mechanism also applied in our real world. So we can predict the future event by monitoring the history of previous events, right? It's the same to the computer architecture. Actually, computer architecture mimic our real world. So prediction also we can apply the prediction mechanism by monitoring the history of the branch instruction. So which means we need store previous results of a certain branch instruction, right? We can detect the branch instruction when an instruction is decoded. And how can we distinguish this branch instruction? We can distinguish branch instruction with the program counter, right? So counter is pointing the address of the instruction. So we can distinguish instruction with the program count value, which means that with the PC, we can figure out the different branch instructions, and then we can store the result of branch instructions, like the history of the branch instruction, by using program counter. Okay, so with the PC, we can point a certain branch instruction, then we can store the history of branch by indexing the PC. But you know, the size of the PC is very large, like 48-bit in a modern computer system. So we cannot use this all PC bits. It's very large. So which means that so we can store the history of a certain branch with the branch prediction buffer called the BPB. But if we use the all bits of the program counter, then this branch prediction buffer will have 2 to 48 entries. It's a very large number. So we cannot use the entire bits in the program counter. We can use the several LSBs in program counter. Okay. So we can index the history of the branch instruction with the LSBs of the PC. So for example, if we use the 10 bits of the PC, then the number of entries in the BPB is the 2 to 10, is the 1024. Okay. So this history is stored in a certain entry of the branch prediction buffer. But we already used the part of the LSBs. What's the problem? There can be aliasing. So which means there are different branch instructions like BR1 and BR2. And then because we used only the parts of the PC, these BR1 and BR2 have the same LSBs, like 100. So even though these branch instructions are different, these branch instructions share the same entry of the branch prediction buffer, which means this is called the aliasing problem. But we can just ignore the aliasing problem because this case is very rare. Okay. So 1-bit predictor is very simple. So which means that we just stores the one previous result. Okay. So we just check the latest result of the branch instruction, and then based on this result, then we just predict the future event of the branch instruction. For example, if the previous result is taken, then we can predict the result of this branch instruction is also taken. And not taken, so it's not taken. It's very simple, but the hit rate may be low. Okay. So for example, so this is the PC of the branch instruction. So we just use the 10-bit of the PC. Then with the 10-bit, then we just store the result of the branch instruction. But each entry of the BPB has the 1-bit data. And then, so the branch instruction is executed with the PC. So which means that we can access the instruction cache with the PC, and then this BPB is also accessed. Then we can get the 1-bit data T. For example, if this 1-bit data is taken, or we can expect that the result of the branch instruction can be taken. Not taken, it's not taken. Okay. But you know, when the double loop is applied, then this 1-bit predictor encounters some wrong prediction for the inner loop. Okay. So in this case, we can apply the 2-bit predictor. So 2-bit predictor means that we can just monitor the 2 consecutive previous result of the branch instruction. Okay. Then we can also use the 2-bit predictor like some saturated 2-bit counter. So which means that the state of the branch prediction starts from the 0, 0, and then 0, 0 is predicted as not taken. Okay, and then when the branch is taken, the state is changed to the 0, 1, and then taken is changed to the 1, 0, the taken is 1, 1, and then just saturated. It's taken, taken, and then not taken, it's going to the previous result. And then based on the state of the branch instruction, the 0, 0 and 0, 1s are predicted as the not taken, and the 1, 0 and then 1, 1 are predicted as taken. So this is the 2-bit predictor. Okay, so which means that we can just monitor the 2 previous result of the branch instruction, and then based on these previous history of the branch instruction, then the result of a branch instruction is predicted. Okay. So these are very simple. Okay, these predictors are very simple, but problem is that sometimes branch instructions are correlated. What does that mean? So let's see this example. So if as statement, you also generate the branch instructions. So if you see that this example, if A equal 2, then A becomes the 0. And then if B equal 2 and B equals to 0. And then this is the third branch instruction. If A is different from B, then what's the... So if we see these 3 branches, like if A equal 2, if B equal 2, and if A is not equal to B, we can find that the third branch instruction is the result of third branch instruction is influenced by the result of 2 former branch instructions, right? So you can find, oh, this code is very weird, but we can find many correlated branch instructions in our code. So this is just some very weird example, but we can find some correlated branch instructions like this. So what does that mean? If this branch instruction is taken, so which means that A equal 2. And then if this branch is taken, this B equal 2. And if this branch is taken, and then also the second branch is taken, the third branch is always not taken. So which means the result of this third branch instructions is influenced by the result of former branch instructions, which means that it's the branch instructions are correlated. So in the previous example, we just learned about the very simple branch predictors. So which means that we can distinguish branch instruction with the PC. So which means that we just monitors the result of branch instructions independently. Okay, what does that mean? We just monitor the previous result of this branch 1 and then branch 2 and branch 3. And then, you know, if we just use this branch prediction buffer, then the result of this branch instruction is not influenced by the result of this branch 1 and then branch 2. Right. But in this example, this third branch 3, the result of branch 3 is influenced by the result of former branch instructions. Okay. So with this independent branch predictions, we cannot cover this case. So which means we can develop them more complex. So which means the result of branch instructions can be influenced by history of global branches. Do you understand? So the result of this third branch instruction is influenced by other result of other branch instructions. So which means the result of this other branch instruction, like branch 1 and branch 2, can influence the result of this branch 3, which means that if we just check the history of global branch instructions, so if we just check the history of branch instructions globally, like if it's taken, can be 1, the bit of this branch predictor can be 1 globally, and then if we just check the second branch, then we can say that, oh, the result of global branch instructions, we just check the history of branch instruction globally. So this is the 1. In this case, the third branch instruction should be always 0. Do you understand? So I mean, this is the global history, global execution, global result of the branch instruction. These global instructions, global result like 1, 1 determines the result of this third branch instruction. Okay, so in order to support this correlated branch instructions, then we can also consider global history of branch instructions. It's a little bit complex. It's more complex than this simple independent branch prediction, but we can find these cases. So in the first page of the branch prediction, then you can find this the execution path in our code. But so if these branch instructions are independent, okay, then we can apply this simple branch predictor. But in our code, we can find the correlated branch instructions. So which means that actually this path, the formal path of the branch prediction, determines the result of following branch instructions. So these correlations are observed in our code, so we can consider the global states of branch predictors. Understand? Okay. So which means that we need to also consider the global history. Also, actually, but the result of the branch instructions are also influenced by local branches, like this one, iteration loop. So which means that we need to also consider the local history of the branch instruction. So which means we can combine the global history or local history of the branch prediction. Okay. So these are called the MNPPB. So what does that mean? So in the previous example, I assumed that global history also influenced the result of the current branch instruction. Also, individual or local branch history also matters. So which means that we need to also distinguish the different branch instructions, the result of different branch instructions. So we can also monitor the global history, the global states of our branch instruction. Also, we can monitor the local history of branch instructions. So this is the MNPPB, so which means that we just check the M previous result of branch instruction globally. So this is the global history registers. So which means that the result of a branch instruction is just registered in this global history buffer, and then these are shifted to the next location at every branch instruction. Okay, so it's just like a shift register. Okay, and the one instruction is one result is input to this shift register, then every element is shifted to the so next location. Then the last element is this is removed from the shift register. So this is the shift register. So we can just monitor the embed history of the global branch instruction, and then also we can monitor the local branch instruction, like with the PC. So by combining global history and then the PC, the part of a program counter of the branch instruction, then we can access the branch prediction buffer. So for example, if this bit is the 10 bit, and then this bit is the 4 bit, then if we just combine the 4 bit and then 10 bit, then these bits can be 14 bit. Okay, so which means the branch prediction buffer will have 14 entries. So, and then with this 2 to 14, this combined index, then we can access the corresponding entry of the branch prediction buffer. So what does that mean? The local branch predictor just distinguishes the different branch instructions like BR1, BR2, and BR3. And then we can know that in the previous example, we can find that these individual branch instructions can be influenced by different branch instructions. So that can be distinguished by global history. So which means if we use the 4 bits for this global history buffer, then which means that we can distinguish 2 to 4 states for each branch. So for example, which means that for this branch one may have 16 different global states, and then we can just monitor the different result for this local branch instruction for 16 different global history or global states. So which means we can also history of the global branch instruction like this. So and then we can combine the global history and then combined with the part of the PC, and then we can generate the MN branch prediction buffer. And if M is P, then we can use the exclusive OR, and in this case, this branch predictor is called G share. Okay, so which means if M is 10 bit and then P is 10 bit, and then if we just apply the exclusive OR for this 10 bit and then 10 bit of the PC, then this branch prediction is called G share. Okay. So then we can apply. So this branch prediction is called the 2-level predictor. So what does that mean? with the global, so with the global branch prediction, so then also we can also focus on the local history of the branch instruction. So we can combine these global branch prediction and then local branch prediction to implement the two-level branch predictors. Okay, then we can distinguish the two-level predictors as the 4 cases because it's obvious because it's a global and then local. So we can access the predictor table with the globally. So we can just access this prediction table with the global history buffer, global history register. And then this case is called the GAG. So in this case, G means the global, and then also you can find the P. So P means that this is the local branch instruction. The P means the per address, and then G means the global. So the two-level predictor, if we apply the GAG, so which means that we just use the global history buffer to access the BPB, the branch prediction table. So what does that mean? We can just check the global history, and then with the global history, then we can access the predictor table. So for example, in the previous example, if N is 4 and then M is 10, right? Oh, no, sorry. So in the previous example, M is 4, then N is 10, right? So N is 10. So in this case, we can just use the 4-bit global history. So which means we can just distinguish the 16 different states for this global prediction table. So global prediction table will have 16 entries. Okay. And then GAP. So with this GAP, then we need to consider the global history register, and then also we can consider the local branch prediction, local branch instruction. So which means if M is 4 and then N is 10, it's called the GAP. So, and then in the GAP, it's the same to this branch predictor. So which means that by combining global history register and then the part of the PC, then we can access the branch prediction table, branch prediction buffer. So which means it will have 2 to 14 entries. Then so this is called the GAP. And then PAG, it's more. PAG means that each local branch instruction has its own history. Okay, so you mean, so if you see this figure, then you can find that, oh, this is the private history table. So which means that each local branch instruction has its own history buffer, and then with the PC, so I said it's a local history. So with the PC, then we can access the private history table, and then based on the result of this private history table, then we can access the global predictor table. So what does that mean? So let's also say this is 10, and then you can just monitor the 4-bit history. So it's like a 4 history of each local. So which means that each branch instruction has 4-bit history. And then based on this history, we can just access the global predictor table. So the result of this private history table will be 4-bit. And then with this 4-bit, then we can access the global predictor table. So this global predictor table has 16 entries. But this 4-bit is assigned to individual branches, right? So this private history table has 2 to 10 entries, but global predictor table has only 16 entries. This is called the PAG. So which means that the history is monitored per address, like some local branch, and then this private history table generate the global history, and then with the global history, then we can access the global predictor table. So actually, the predictor not globally. Each branch instruction has local history, and then with the local history, then we can access the global predictor table. So it's called the PAG. Another extreme case is the PAP. So which means that each local branch instruction has its own private history register. So we can access this private history table with the PC. And then by combining this private history and branch PC index, like each branch instruction, then we can access the private predictor table. This is called the PAP. So this is the most expensive two-level branch predictor. So what does that mean? With this branch PC index, then we can access the so n is 10. Then the entry of the private history table is the 2 to 10. Now 1024. And then each entry may have the 4-bit history. And then with this 4-bit history, by combining this 4-bit history and also another 10-bit of this PC, then we can access the private predictor table. So which means this private predictor table has 2 to 14 entries. Okay. So when we mention the two-level branch predictor, the first letter represents the history, and then the last letter represents some per address or global. So access how the predictor table is accessed. Okay, so this is the two-level predictor. So actually, this branch prediction is relatively simple, but if we just consider the history of the global branch or local branch, then the branch prediction becomes more complex. So sometimes, yeah, so it's more complex. Okay. Another approach is we can combine the different kinds of predictors. So it's more complex. So actually, the different predictor can be applied to different kinds of branch instructions. So, and then the problem is that, so so if we just consider this independent branch instruction, then the simple branch predictor can be better. So the problem of this complex branch predictor is that not monitor the previous result, then it will take a long time until the branch predictors are stabilized. So what does that mean? If we use very complex branch predictors like the PAP, then the history for local branch instructions, also history for this private predictor table should be collected. But in order to collect the enough previous result for some different states of these local branch instructions, it will take very long time. So if we use the very complex branch instructions, then the hit rate may be higher than the simple branch predictors. But the problem is that until the branch predictor becomes stable, maybe until the branch predictor collects the enough previous result, then the complex branch predictor will take more cycles or more time. So it takes time until the enough results are collected. So that is the disadvantage of the complex branch predictors. So we can combine different kinds of branch predictors, like the predictor 1 and predictor 2 and predictor 3. So if there are 3 different kinds of predictors, then these predictors may generate the different prediction result, like it's taken, or it's not taken. It's like a boat. So there are 2 takers and then 1 not taken. So it's like voting. So then we can find that, oh, these 2 predictors predict as taken. So we can predict like taken. Okay. So we can combine the different kind of branch predictors. Also, we can also increase some hit rate of the branch predictors. So it's a little bit more complex. So which means that we need to invest some more hardware resources to implement the different kinds of branch predictors. Okay, in this case. Okay. This is the end of branch predictors, but recently also maybe 10 years ago or some many researchers also focus on the performance of the branch predictors. So which means that researchers try to increase the hit rate of the branch predictors. Okay. But recently the performance of the branch prediction is also saturated. So which means that we can use the very good branch predictors. Okay. But increasing the hit rate is also critical. So which means that, and then it's just a prediction. And recently, we can apply some machine learning techniques for these branch predictors, right? If we also some researchers also focus on applying machine learning techniques on the modern branch predictors. So, but the problem is that if we apply the machine learning techniques, then we need to train the branch predictors. Also, the machine learning techniques may require more hardware resources. Okay, but so it's a machine learning error. So we can apply some new machine learning algorithm for improving the performance of branch predictors. Okay, another required hardware resource is a branch target buffer, but it's very simple, right? Because when the branch instruction is executed, BQ, and then sorry. Hey. For the conditional branch instruction like PQ, so there's the condition, and then this is target of the branch instruction. So for the most of conditional branches, then the target of the branch instruction is fixed. So which means that if we just first know the target of the a certain branch instruction, then we can easily predict the target of the branch instruction. And then we just use this target when the branch instruction is taken. So if we just know the target of the branch instruction first, then if we just store this target using this some LSB part of the PC, then we can use this target. So this is the branch target buffer. So there can be aliasing problem also in this case because we use the part of a program counter for this branch target buffer, but we can use the tag like that. So we can build the branch target buffer like cache. So which means we can also store the tag in the branch target buffer, and we can check that this PC is the same to the PC that stores that is stored in the branch target buffer. Okay, you can apply the cache-like approach to the branch target buffer, and it's very simple. Okay, but if we use the jump instruction and then like JAL, the jump and link instruction. So we use this jump and link instruction for functions or procedures. So when this jump instruction is executed, then the return address array is called the array is stored in the registers. And then if we use the jump ARL, so which means that this instruction jumps to the return address. So what does that mean? For this return instruction, so we frequently use this JALR, so actual return. So we frequently use this instruction for procedure, and then when a function returns when a code is returned from a sub-function, subroutine. So in this case, the target is not fixed, right? This target is not fixed. So in this case, it is not easy to use the branch target buffer for the return. So in this case, we use the return address stack. So the function is called from the parent function, then it's called like called and called and called. So and then actually the return address is stored and stored and stored. So then actually this return address is stored in the return address register called the array. So if we just apply the stack like hardware component for this return address stack, then we can estimate some target of this return function, right? So for the specific type of the jump instruction, then we can apply the return address stack. But these are also predicted value. So if the prediction is wrong, then we need to roll back the execution path of this return address. Okay. So this is the end of the branch instruction, branch predictor by combining ROB and then branch prediction buffer, branch target buffer, and register alias table. Then we can apply the speculative execution here. And register renaming. Okay, so we are still here. Then another technique is the speculative scheduling. And then, this is relatively simple. So actually, so I hope you can understand. So as I mentioned, the speculative execution is the very important part of this course. So try to understand about this speculative execution. Like, and then, we can implement the speculative execution with the branch predictors and reorder buffer. Okay, and then also register alias table. And then the next technique is the speculative scheduling. And then, we can understand that the speculative scheduling is similar to the data forwarding. Actually, it's just relatively simple. So what's the problem of the register renaming and speculative execution? So the problem is that this path is long. So, actually the one stage is included in the pipelining of the out of the processor, then the latency of the execution gets longer. Now how can we improve this performance? How can we solve this problem? If the latency is long, so which means that after the data is delivered to the common data bus, then after one cycle, then a certain instruction can be issued. So which means that it's very similar to the following instructions can be executed after the previous result is written back to register file. The five-stage pipeline architecture, it's very similar to this is the register file, and then there is no data forwarding path, and then after this data is written back to the register file, then the following instruction can read the data from the register file. So what is missing? So we don't have data forwarding path, but with the data forwarding path, then we can solve the data hazard, like the low hazard actually. So with the data forwarding, then we can reduce the wasted clock in the static pipeline. But the problem with register renaming is that after CDB, so it's actually write back. After write back, so we can use the data from the physical register file. The speculative scheduling means we can apply the data forwarding in the out of the processor. Then how can we apply the data forwarding in the static pipeline process? We can apply data forwarding because we know the exact latency of execution unit, right? Because we know the exact latency. So exact clock cycles of execution unit, then we can apply the data forwarding. And actually, like these execution engines, the latency is fixed. So we already know the latency of these execution engine. So which means that we can know when an instruction is issued to this instruction unit, that we can expect when the result is ready. So for example, if the instruction is issued to the integer unit, then we can get the result after one cycle. In the floating point unit, then we can get a result in 5 cycles. Right? Because these execution engines have fixed clock cycles. So, which means that if we know the exact timing of when the results are ready, then we can forward these data to the forwarding path. Okay. So the main idea is that instead of issuing instructions after the former instruction, the result is delivered to the seed common data bus. We issue these instruction by predicting when the required operands are ready by former instructions. So similar to the data forwarding, right? So just to see that this timing diagram. So we can say that, oh, this load instruction, so for this load instruction, the data will be delivered to the common data bus at clock cycle number 7. But when the data is ready, so actually this data, so this F1 data is required by execution engine. So, and then data is read from the cache at clock cycle 6. So this data can be forwarded to the execution engine at clock cycle 7. It's data forwarding, right? Which means that this add instruction can be issued at clock cycle 5. Then, so register fetches in 6, and then this data is forwarded to the execution engine at clock cycle 7. Okay. So speculative scheduling means that because since the latency of this execution engines are fixed, then we can forward the data to the input of the execution engine. And then based on this scheduling, then we can issue the instruction before the data is delivered to the common data bus. Okay, so this is bypass part is inserted in this register fetch stage. The problem is that actually this load instruction access the cache, but we already know that the memory instructions have various latencies based on the cache hit or misses. So in this case, so actually in this timetable, we assume that this load instruction is hit in the data cache, but actually we cannot know when the data is ready for this add instruction. So in order to avoid this case, we can implement the simple replay queue like this. Also, this is some speculative scheduler that wake up the instruction in the issue queue based on some predicted timing of when the operands are ready. But if this prediction is incorrect, then we can apply the replay queue, and then we can also check the data from the register file. Okay. But I believe we can simply apply this speculative scheduling only for the arithmetic or logical instructions, not memory instructions. That's fine. We can then we can until the data is ready in the register file for only for load instructions. That can be possible. Okay. So with the speculative scheduling, then it's very similar to the data forwarding. So actually we can implement the data forwarding with the speculative scheduling. Okay. It's a simple. And the value prediction. Value prediction is a very aggressive prediction, actually. So which means that we use, actually the computer use the many values, but we can, sometimes we can expect some values of instructions. Like we frequently use the same value, like the constant data, or we can use the incremented value like I plus plus, so it's I plus I equal I plus 1. Also, some values have the same stride, like 0, 2, 4, 6, blah, blah, blah. So if we just access some indexes, then we can find some fixed stride. Except some values are very predictable. So we frequently use the value zeros and ones. So in our instructions, some values are very predictable. Then, so which means that even though some value is not ready, we can use the predicted value. This is the value prediction. It's a kind of branch prediction, right? We don't know the result of the branch instruction, but we can apply the prediction. So value prediction means that we don't know the value, this value, but we can predict the value, then this instruction can be predicted. So if we apply the value prediction, then we can handle the predicted instruction like the predicted branch instruction, right? So this is a very aggressive prediction mechanism, processor. Okay. Okay, so so I will stop here, and then so now so in the next class I will briefly summarize the out-of-order process architecture. Also I will explain about some superscalar implementation in the out-of-order process architecture. So actually the modern processor applies the out-of-order processing, speculative execution, and the superscalar. Okay, so our most of high performance processor applies these three techniques in our process architecture. Okay, so also as I mentioned repeatedly, this part is very critical part of this course. So please try to understand about the mechanism of out-of-order processor. Okay, so I will stop here. If you have any, do you have any questions? Okay, so see you in the next class, and then we will provide the in-person lecture for the next class. Okay. Okay. Thank you guys, and then see you in the next class.